Today we will start with phenols. We have already done its preparation and what are phenols. So next is its chemical properties. First is ether formation, that is the reaction in which only H of phenol is replaced. And thus if we treat sodium phenate or sodium phenoxide with methyl iodide and we heat the mixture, then this methyl group replaces sodium and we get ether, that is C6H5OCH3, and it is we get C6H5OCH3, it is methyl phenyl ether, methyl, then it is phenyl and OS ether group, so methyl phenyl ether plus sodium iodide. Similarly, if we take sodium salt of phenol, that is potassium phenoxide, then it is treated with alkyl halide, any alkyl halide, so suppose it is ethyl bromide, then we similarly get KBr is removed and this ethyl group, these ethyl groups replaces the potassium and we get ethyl phenyl ether. So the reactions in which we get sodium phenate or potassium phenate with alkyl halide in the presence of heat to give ethers, these reactions are called Williamson synthesis. This reaction is Williamson synthesis. And similarly, if we treat sodium phenate with allyl halide means to the carbon to which alkyl halide is attached, to the next carbon double bond is present, that is next carbon next to the double bonded carbon has halogen group attached to it, so it is allyl halide and it is particularly allyl bromide. And thus when it is heated, then this allyl group, full alkyl group replaces sodium and we get allyl phenyl ether and sodium bromide. So these sodium or potassium salts of phenol, when treated with alkyl halides or aryl halides to give ethers, this reaction is called Williamson synthesis. This reaction is called Williamson synthesis. Williamson synthesis reaction can be asked separately in naming reactions also. So, but in this, if we have taken aryl ether, that is the reaction with allyl ethers, allyl halides, and that we get aryl ethers. When these are heated in the presence of inert solvent such as diphenyl ether at 475 Kelvin, it undergoes a rearrangement. That rearrangement is called Claisian rearrangement, in which the allyl group migrates to the ortho position or it migrates to the para position. It depends upon the conditions. So the rearrangement in which allyl group migrates to the ortho position or to the para position when it is heated in the presence of inert solvent such as diphenyl ether at 475 Kelvin, then that rearrangement is called Claisian rearrangement. That is this is allyl phenyl ether at the presence of 475 Kelvin. It gives ortho allyl phenol, that is allyl group migrates to the ortho position. So when ortho positions are free, then this group migrates to the ortho positions. If ortho positions are occupied, then allyl group moves to the para position. So first take up, when these ortho positions are free, then this group moves to ortho position, and in that case the mechanism is it is an example of pericyclic reaction which involves this cyclic transition state in a mechanism. In this, these pi electrons form bond with this carbon, and these pi electrons move between these carbons, and so these electrons move to this oxygen, and we get this cyclic transition state. In this cyclic transition state, this bond is OC bond is in the process of formation break, or in the process of breaking, so it is shown dotted, and this one single bond is already present and second bond will form. So this second bond, which is in the formation process, is shown in dotted line, and then here there are two double bonds, one will break, so one is shown in dotted, and in this here one bond will form, so this is again shown in dotted, and the pi electrons or the bond of benzene ring will break, so it is again in dotted. So and here one bond is already present, one will form, therefore here again a dotted line. So this structure, cyclic transition state, is a part of mechanism in which further there is double bond formation, double bond O. H is already present in the ring, is shown just separately because this bond has to be involved in further, and this is allyl group. So what is important is the order in which carbons are present at the ortho position. In this, as we see in starting reactant, alpha carbon was attached to oxygen. Alpha carbon is attached to oxygen, and gamma was away from that carbon. So, but when the formation takes place, the alpha is away from the ring and gamma gets attached to this ortho position, and finally these electrons move to ring, here is double bond, and these electron moves to oxygen, and hydrogen moves to this, and we get OH. And the order is, in the starting alpha was attached to the ring, now this allyl group gets attached to ring by gamma carbon. It is important, gamma carbon is attached to this ortho position, so it is ortho allyl phenol. Similarly, if the ortho positions are occupied, then this group will move to, these both positions are occupied, then this allyl group will move to this para position, that is this. So in the starting reactant, this alpha carbon is attached to the oxygen, and in the product, because these both ortho positions are occupied, through the gamma carbon it gets attached to the benzene ring in the ortho, but in this carbon is not attached, but in this alpha remains the first carbon. So in para In para attack or para rearrangement, this allyl group again binds through alpha carbon only to the ring. For its mechanism is first as such CH2 CH double bond CH2. These carbons are marked as alpha, beta, then gamma. At 475 Kelvin, when it is heated, as already done, these electrons will move to this, these will electron moves to this, and these will electron moves to this. That is, here there is bond formed between ring and carbon, and then double bond O, here double bond O, and the hydrogen present is also shown as such in the ring. Now again this rearrangement will further take place, that is this group will move towards the para position. This will move to para position, that is now you can see alpha carbon again gets attached to this para carbon, and gamma carbon is away from this. So the starting reactant also had alpha at the starting, and the last final will also have alpha carbon at the starting, that is attached to the carbon. So there is 2 times inversion takes place. First here is alpha, here gamma, then again alpha. So finally this carbon or hydrogen gets detached, and these electron moves to ring, these electron moves to ring, and this to this, and hydrogen gets attached to this oxygen. So we get OH. These are CH3 ortho positions occupied shown, and this is the allyl group. So allyl group moves to the para position. So next is, we can say in para one inversion is followed by another inversion, and therefore there is no net inversion in para. So it's important, it can be asked how you can write the mechanism for para position when both the ortho positions are occupied, and how you can show that no net inversion takes place. So next is ester formation. When phenol is treated with acid chloride or acetic anhydride in the presence of pyridine, acid chloride or acetic anhydride, we get only HCl is removed, and this whole group gets attached to oxygen, that is we get ester, COOR group, that is phenyl propanoate, because 3 carbons are present in the side chain. And similarly, when it is treated with acetic anhydride, again this whole group gets attached to oxygen, and hydrogen from this gets attached to this, and we get acetic acid. So it is formation of ester, in this case phenyl acetate. In this, if this phenyl acetate is, or phenyl ester, is treated with anhydrous aluminium chloride in the presence of acid or acidic water, this phenyl group, this acetyl group moves to ortho or para position, and this arrangement is called Fry's rearrangement. That is, this group moves to ortho or para position. At low temperature specifically, that is below 333 Kelvin, para isomer is a major product, and at high temperature ortho is a major product. So we see its mechanism. In mechanism, first, phenyl acetate already formed in earlier reaction we have seen. When it is treated with anhydrous AlCl3, AlCl3 is electron deficient, so it gets attached to oxygen like this. Now it has negative charge and oxygen will have positive charge, and then it's in equilibrium with this acetyl group. This acetyl group is released, and this acetyl group will have C double bond O. C will have positive charge and O has two lone pairs. It is resonance stabilized with CH3C triple bond O positive. That is, if a lone pair moves to this, there will be a triple bond and oxygen will be neutral, and now carbon will be neutral, and then now oxygen will have positive charge. So it is a acylium ion and is the resonance stabilized. These ion then attacks this compound through the carbon. Carbon has positive charge. So these electrons gets attached to this. Through this, it forms bond with benzenic at the ortho position, and the electrons of oxygen moves to ring, and there is a double bond, and this acyl group attached to ortho position. Ortho position already has hydrogen, which is shown here as H, and now in the next step, this hydrogen will release its electron to the ring, and these electron goes back to oxygen. So oxygen is now neutralized, and there is double bond, ring has double bond, and this COCH3 group is attached to ortho position. Then with water, this AlCl3 Cl2 is removed, and we get OH, and here is acyl group, so it is orthohydroxy acetophenol. Similarly, for the para attack, we see acyl group attacks on the para position. For this, these pi electrons form bond with carbon, and these electrons move to this next position, and these two ring, that is O double bond, and there are two double bonds outside, and this para position has acyl group, and para position already has hydrogens. It is shown in this. And when further these electrons, hydrogen is released, electrons go back to ring, these to this, and these electrons to oxygen, and we get this acyl group at the para position. And then with water, upon hydrolysis, we get para hydroxy acetophenol, that is aceto group is attached to the para position. So it is para hydroxy acetophenol. So these two reactions were the reactions in which only H of phenol group is replaced. First is ether formation, second is ester formation. Both are important with their rearrangements. Mechanism of rearrangements can be asked. So next is reaction in which OH group is replaced, and OH is replaced with hydrogen. That is when it is treated with zinc dust, we get benzene and zinc oxide, that is OH group is replaced with hydrogen, so it is benzene and zinc oxide. So this is all about the reactions in which OH group of phenol is involved. So next we will start with electrophilic aromatic substitution reactions of phenol. Thank you.